everyone, this is Chinnaiah Kalpana here. In this video, we are going to solve an equation from higher order linear differential equation. So let's get going. Problem. Solve dq plus 1 into y equals to e power x plus 1 whole square. Solution. Given differential equation, dq plus 1 into y equals to e power x plus 1 whole square, which is an operator form. F of d into y equals to q. By comparing these two equations, we'll get f of d and q, right? Where f of d equals to dq plus 1 and q equals to e power x plus 1 whole square. So, actually, firstly, we have to find the order and degree of the given equation. So, let's find now the order and degree of the given equation. Okay, you can write the given equation as d cube into y plus 1 into y is y equals to e power x plus 1 whole square. We know that d is a differential operator, which is d by dx. Then d square is d square by dx square. You can write d cube as d cube by dx cube, right? Then you can write d cube y as d cube y by dx cube plus y equals to e power x plus 1 whole square. Now identify the highest derivative here. D cube y by dx cube is the highest derivative, so our order will be 3, and the highest power of the highest derivative is the degree. So here degree is 1. Fine. Now we need to find the general solution to the given non-homogeneous equation, right? So the general solution is given by y equals to yc plus yp, where yc is a complementary function obtained by roots of auxiliary equation of the homogeneous equation of the given non-homogeneous equation. Simply by considering RHS part to 0, we'll get the homogeneous equation, right? And we'll find yp using 1 by f of d into q. So let's find complementary function firstly. Using the auxiliary equation. The auxiliary equation of f of d into y equals to 0 is f of m equals to 0, where f of m equals to, we are having f of d equals to d cube plus 1. So let's replace differential operator by m. Then you'll get f of m equals to m cube plus m. Then our auxiliary equation will be m cube plus 1 equals to 0. We have auxiliary equation m cube plus 1 equals to 0. Now we'll find roots. So we'll find roots in two different ways. Okay, I'll show one by one. So firstly, let's find using synthetic division method. For m equals to 1, minus 1, 2, minus 2, and so on. So here you're having m cube plus 1. Okay, by looking at this, we can say that m equals to minus 1 satisfies the polynomial. The polynomial m cube plus 1 becomes 0 when m equals to minus 1. Okay, firstly, let's see for m equals to 1. What happens if m equals to 1? You'll get 1 cube plus 1 equals to 1 plus 1, which is equals to 2, right? So this is not equals to 0, which means that m equals to 1 does not satisfy this polynomial. Now let's try for minus 1. Minus 1 whole cube is minus 1 plus 1 equals to 0. So we can say that m equals to minus 1 satisfies this polynomial, right? So what we'll do is, we'll place the quotients of m's. Here 1 is nothing but 1 into m power 0, right? So the quotient of m power 0 is 1. And you don't have any quotients for m square and m, so put 0. And quotient of m square is 1, right? For m equals to minus 1, since minus 1 satisfies this polynomial, right? 1 plus 0, 1. Minus 1 into 1, minus 1. 0 plus minus 1 is minus 1. Minus 1 into minus 1, 1. 0 plus 1, 1. Minus 1 into 1 is minus 1. 1 minus 1 is 0. Again, here, with these three numbers, you'll get another polynomial, m0, m1, m square, right? From m equals to minus 1, you'll get m plus 1 equals to 0. That means m plus 1 is 1 factor, right? You can write m cube plus 1 as product of 1 factor into the fraction obtained from these three numbers. That is, the polynomial obtained from these three numbers is m square, not fraction, okay? From these three numbers, we'll get another polynomial m square minus m plus 1. So you can write m cube plus 1 as m plus 1 into m square minus m plus 1. Okay. So what happens if you put m equals to 1, you'll get 1 minus 1 plus 1 equals to 1. Again, you got not equals to 0. We have to get equals to 0, right? When you put some m, the polynomial should get satisfied. That means you'll get equals to 0. If you put m equals to minus 1, you'll get minus 1 whole square, minus of minus 1 plus 1 equals to 1. Minus into minus plus 1 plus 1 equals to 3, right? So it seems it won't get satisfied for any of these m's. So what we'll do, we will, let me write m square plus 1 as product of m plus 1 into m square minus m plus 1 equals to 0. If you want, you can check. Is equals to m into m square minus m plus 1 plus 1 into m square minus m plus 1 equals to m into m square, m cube minus m into m square plus m into 1, m plus 1 into m square minus m plus 1, right? So here minus m square plus m square gets cancelled, plus m minus m gets cancelled, and finally you'll get m cube plus 1, the same thing. Okay, now what we'll do is, equate each factor to 0. You'll get m plus 1 equals to 0. M square minus m plus 1 equals to 0. From this, you'll get m equals to minus 1 root. And you need to find root from this, which is in, here we are having an equation which is in quadratic form, right? That is am square plus bn plus c equals to 0. So here we can use quadratic equation to find the roots. M equals to minus b plus or minus square root of b square minus 4ac by 2a, right? Now compare coefficients or both the equations, then you will get a equals to some 1, b equals to coefficient of m minus 1, c equals to constant 1. Okay, now substitute the values of a, b, c in this m, then you will get minus of minus 1 plus or minus square root of b square minus 1 whole square minus 4 into a, 1 into c, 1 by 2 into 1, which is equals to minus into minus plus 1 plus or minus square root of minus 1 square is 1 minus 4 into 1 is minus 4 by 2 into 1, 2, which is equals to 1 plus or minus square root of 1 minus 4 is minus 3 by 2. right? We got m equals to some 1 plus or minus square root of minus 3 by 2, right? Again, you can split minus 3 as square root of minus 1 into 3 by 2, right? Again, you can write square root of minus 1 into 3 as square root of minus 1 into square root of 3 by 2. We know that I equals to square root of minus 1, right? So we can replace the square root of minus 1 by I. Then you'll get 1 plus or minus I root 3 by 2, which is equals to 1 by 2 plus or minus I into root 3 by 2, which is a complex number or complex conjugate, we can say. If 1 by 2 plus I root 3 is a complex number, then its conjugate will change the sign in the middle, right? Then you'll get 1 by 2 minus I into root 3 by 2. So we call these two numbers as complex conjugates. Fine. Then we'll get m equals to 1 by 2 plus or minus I into root 3 by 2, right? For this. Then the roots of m cube plus 1 equals to 0 is m equals to minus 1, and from m square minus m plus 1 we'll get 1 by 2 plus or minus I into root 3 by 2. Okay, we'll get complex conjugate numbers, or two complex numbers we can say, and one distinct number. Okay, from m square minus m plus 1 equals to 0, we'll get m equals to 1 by 2 plus or minus I into root 3 by 2. Let it be. Now we'll see another method to find roots. Consider m cube plus 1 equals to 0. You can write this 1 as 1 cube, which is in a cube plus b cube form. We know that a plus b whole cube equals to a cube plus b cube plus 3ab into a plus b, right? Or you can just write this as a cube plus b cube plus 3ab into a plus b equals to a plus b whole cube. Okay, now take this term to RHS, you'll get a cube plus b cube equals to a plus b whole cube minus 3ab into a plus b. If you notice, we are having a plus b in both the terms. So let's take a plus b common from RHS. We'll get a plus b into a plus b whole square minus 3ab, right? We can expand a plus b whole square, then you'll get a square plus b square plus 2ab minus 3ab. From this we'll get a plus b into a square plus b square plus 2ab minus 3ab is minus ab, right? Since a cube plus b cube equals to a plus b into a square plus b square minus ab. So what you can do? Simply, for a equals to m and b equals to 1, you will get m plus 1 into m square plus 1 square, 1 minus ab, that is m into 1, m equals to 0, right? Again, you can write this as m plus 1 into m square minus m plus 1 equals to 0. Now, by equating each factor to 0, you'll get the roots, right? When m plus 1 equals to 0 and m square minus m plus 1 equals to 0. When m plus 1 equals to 0, you get root m equals to minus 1. And when m square minus m plus 1 equals to 0. You will get m equals to 1 by 2 plus or minus I into square root of 3 by 2. Right? Then m equals to minus 1 and 1 by 2 plus or minus I root 3 by 2. Okay? You can use any of these two methods to find the roots. These are the two possible ways. Fine. Now, let's write the complementary function. So here are the roots of f of m equals to 0, right? Which are one distinct root and okay, no problem, which are one distinct root and the remaining is complex conjugate. Okay, one is distinct and this is a complex conjugate. Fine. Now we know that when you have a distinct root, okay, say m1, then our solution is some constant into e power that distinct root into x. What happens if we have some complex conjugate roots, say m2 plus or minus I into m3, then we'll have, we can write like this. Actually, if you have a plus or minus ib, then e power ax into c1 cos, here you have already used c1, right? So let's use c2. c2 cos bx plus c2 sin bx, right? If you have both roots, then you'll add these two. Then our complementary function will be yc equals to, for distinct root, you'll get c1 e power minus 1 into x plus, for complex conjugate root, you'll have e power 1 by 2 into x into, you have used already c1, so let's write another constant, c2 cos root 3 by 2 into x plus another constant c3 into sine root 3 by 2 into x, right? Which means yc equals to c1 e power minus x plus e power 1 by 2 into x can be written as x by 2 into c2 cos root 3 by 2 into x is x root 3 by 2 plus c3 into sine root 3 by 2 into x is x root 3 by 2. Right? They were yc. Now let's find yp. Particular integral is given by yp equals to 1 by f of d into q. We have f of d dq plus 1 into q e power x plus 1 whole square. E power x plus 1 whole square. Let's expand this using a plus b whole square formula, which is equals to a square plus b square plus 2ab. We'll get e power x whole square plus 1 square plus 2 into e power x into 1, which is equals to e power x square can be written as e power 2x plus 1 plus 2 e power x, right? Then you get 1 by dq plus 1 into e power 2x plus 1 plus 2 into e power x. You can again write this as 1 by dq plus 1 into first term plus 1 by dq plus 1 into 1 second term plus 1 by dq plus 1 into third term 2 into e power x. Then yb equals to 1 by dq plus 1 into e power 2x plus 1 by dq plus 1 into, you can write this 1 as e power 0 into x, or write 1 itself, we can change it afterwards, and write 2 first in the third term into 1 by dq plus 1 into e power x. Right? Now we can find each term separately, or you can name all these three separately. First term can be represented by pi1, second term by pi2, and third term by pi3. So first we will find pi1, which is 1 by dq plus 1 into e power 2x, right? We have f of d equals to dq plus 1. Now let's find f of 2. Here you're having q equals to e power ax form, where is a real number. Find f of 2, you'll get 2q plus 1 equals to 2 cube 8 plus 1 equals to 9, which is not equals to 0. Since f of 2 is not equals to 0, so we can apply the value of 2 in d, or replace d by 2, or you can simply write f of 2. Since f of 2 equals to 9, right, equals to 1 by 9 into e power 2x, which is equals to e power 2x by 9. Here, instead of writing f of 2, you can write some 1 by 2q plus 1, okay, into e power 2x, or you can write f of 2, there is nothing wrong in it. So therefore pi1 equals to 1 by dq plus 1 into e power 2x equals to e power 2x by 9. Now let's find pi2. pi2 equals to 1 by dq plus 1 into 1. You can write this 1 as e power 0 into x, right? Now for a equals to 0, let's find f of 0, which is equals to 0 plus 1 equals to 1, which is not equals to 0. Since f of 0 is not equals to 0, so what we can do, we can replace d cube by 0, you'll get 0 plus 1 into e power 0x, which is equals to f of, okay, 1 by 1 into e power 0x, which is equals to 1 into e power 0x is e power 0, which is equals to 1, right? Since e power 0 equals to 1. Or we can just write here, instead of writing 0 plus 1, you can write f of 0, okay? Since f of 0 equals to 1, we can replace f of 0 by 1 into e power 0x becomes 1 into e power 0, which is equals to 1. So therefore, pi2 equals to 1 by dq plus 1 into 1 equals to 1. Now let's find pi3. 2 into 1 by dq plus 1 into e power x. Now for a equals to 1, find f of 1. We'll get 1 plus 1 equals to 2, which is not equals to 0. Since f of 1 not equals to 0, so what you can do, we can just replace d by 1, then you'll get 1 plus 1 into e power x, which is equals to 2 into 1 by 2 into e power x. 2 gets cancelled, equals to e power x. Or you can just write this as 2 into 1 by f of 1 into e power x. Instead of writing this, you can write this step, 2 into, replace f of 1, since f of 1 equals to 2, then you'll get e power x. Therefore, pi3 is 2 into 1 by dq plus 1 into e power x is e power x. Now let's write yp. Now coming to particular integral. Then particular integral becomes, result obtained from pi1 is e power 2x by 9 plus result obtained from pi2 1 plus result obtained from pi3 is e power x. Therefore, yp equals to e power 2x by 9 plus e power x plus 1. Then the general solution is given by y equals to yc plus yp. Then y equals to yc, you are having yc equals to c1 e power minus x plus e power x by 2 into c2 cos x root 3 by 2 plus c3 sine x root 3 by 2 plus yp e power 2x by 2, 9 plus e power x plus 1, which is the required solution. So we have seen a problem from higher order linear differential equation in this video. Hope you'll understand. We'll see you in the next video. Until then, bye bye.